Recovery. I did a couple of slides already, and I think I stopped at message logging, which was this one. There's a fun part to this, but you got to learn to appreciate it. It's the last slide, actually. Okay, so let's see where we were last week. We're all now in so-called recovery mode. In order to recover, you take checkpoints. Having checkpoints allows you to roll back, and then the only issue with distributed systems is to make sure that the different processes that constitute a, let's say, distributed application have built a consistent recovery line. And I define consistency as that every message that has been checkpointed as having been received has at least a known sender. Okay? And okay. Now, the issue, a potential issue with taking checkpoints is that it may involve a lot of state. And if you have a lot of state to checkpoints, that means that basically you're writing everything to disk. That may really be a bottleneck in your recovery, or to support recovery. So the whole idea is, can I do with less? And with message logging, what you try to do is you take a checkpoint, and then at a certain point you record important activities of your application, and you replay bits and pieces of that. And the most important thing that I'll be talking about is trying to replay messages, and what I'll try to, sending and receiving of messages, and what I'll try to make clear is that that's the only thing you need to do. Apparently these people were in the wrong room. Took them almost a minute to discover this. That's also interesting. Okay. So the whole idea is to, instead of just taking full-blown checkpoints, you replay your communication behavior, and that's it. Now, the assumption here is that you're assuming something like piecewise deterministic behavior, a so-called piecewise deterministic execution model, which is a fancy way of saying that you have a process, and every process is just a bunch of instructions. You can chop them up in segments, and in each of these segments you have a bunch of instructions that are essentially only executed on that machine, no external interference, and most important is you can just replay them over and over again, and you will always see the same behavior. A very stupid example is a bunch of instructions that simply add two numbers. Okay? Hopefully, when you repeat those statements over and over again, you will always see exactly the same behavior, regardless of what's going on in your environment. Now, so this is one important assumption, that the execution of each process can be considered as a sequence of state intervals, and every state interval starts with a non-deterministic event. For example, the message receipt. So here you say, okay, hey, I'm going to start a brand new part of my life, and the execution in such a state interval is completely deterministic, like adding a bunch of numbers. Up to the point that you either send a message or that you receive a message, because these things are considered as external events. And by logging then the external events and replaying the parts that are completely deterministic, you actually can get a complete replay scenario. Okay? That's the basic idea. So the whole idea is that if you record the non-deterministic events, like sending and receiving messages, you obtain a deterministic execution model of the entire distributed application. Got it? So, why is logging only messages not enough? And actually, it's not that difficult if you think about it. Yes? There can also be interrupts. Okay, let's think a bit about this. So that's right. Are all interrupts important? Can you give me an example of an interrupt that is important? or that could be important?
When something went wrong, the kernel gets trapped like, oh shit, something went wrong. Which is an interrupt.
That's an interesting one. Okay, let's put that one on hold. It's a very, very interesting example. Yes. Oh, I have to repeat this, by the way. When the operating system says, "Oh, yeah, something went wrong," and then it will generate something like a segmentation fault, for example. Yes. You have to log in the begin state. But give me. We'll log the begin state. So I want to have a running program that communicates with other programs, and I would like to have an example of something that you may also need to log, because it is essentially, this is the crux, a non-deterministic event. Yes.
Your hard drive, perhaps, because then the execution of the program becomes dependent on the contents of your drive.
Yes and no. Yes, if you're the only one. No, yes, if you're not the only one. And no, if you're the only process on your machine, what you'll be writing to your hard disk is completely deterministic, and also what you'll be reading from your hard disk, right?
If, for example, the application changes, the code division connect or changes the connection cell.
Yes. So if the application would change a port or the connection, that's true. That's all related to communication. So I'll make my question a bit more precise. Are there non-communication related events that you would also need to record? Some kind of? No, not something like sequence number or priority numbers. So let's move on to what the two of you actually said. Suppose you have multiple processes, and you have an operating system that provides you with multiple processes. Now you can have a clock interrupt, and the clock interrupt may lead to the scheduling of another process. Okay? The big question is, do I need to record that event? I have full control over the operating system. I can log anything I like. Actually, it's an important. So the question is, do you have anything to say over the operating system? That's basically what you said. I can be in full control of the operating system. Would I have to log such an event?
Yes, if your operations which your process is executing are dependent on some other process.
Yes, if your events are dependent on the execution of some other event. I think that's the correct answer. So it's not a yes or no. It in the end matters to what extent there are dependencies on other processes that may not or may have been captured by communication that will determine a different execution than the one that you could predict. This is kind of a... So I'll give you another example. If I'm just doing my add instructions and I get a clock interrupt, then when I get the CPU back, I'll just continue with my normal executions, right? But matters become a bit tricky if I'm accessing shared data. Now, you could argue that this is basically communication. If it's communication, then I say, hey, we're withholding that actually. So it's a bit subtle. Now let's take the segmentation fault also as an example. Would you have to record that? Well, the interesting thing is, with a fully deterministic system, no communication, completely isolated, no randomness, okay? And watch out what I mean by randomness. I'll explain that in just a minute. You can bet your life on it that if you would replay your program, it will run instantly into the same segmentation fault. So no need to record it. If you have randomness, that's the non-determinism, well, then things become more difficult. And if your randomness, for example, depends on an external event like the value of a clock, now you need to start recording certain things. If your randomness is based on a random number generator, that thing is completely deterministic. And then you don't need to record it. Got it? And to keep matters simple, let's just assume that only sending and receiving messages is what makes the whole thing go. And is then logging only non-deterministic events enough? Yes. Okay? Okay. Now, what's the whole idea with this whole message log? We'll just concentrate on logging messages because that's, of course, the most important thing. When should you actually log messages? And this is going to be the theme of the rest of this chapter. And the whole issue is that I'm sorry about this, but you got to avoid orphans. Okay? I made some small adjustments to the slides, not corrections, but to make sure that if you look at the slides, that the information is also on the slides. I think, you asked me last week the question, basically, how should I study this material? I advise everyone, take the slides as your starting point. Okay, study those first. I consider the slides as a pretty good summary of what's in the book, actually. That's the reason why the slides are the way they are. They violate all the rules of so many lines on the slide, but I don't care about that. If you do it like this, and then you go back to the book, that should give you a very complete coverage of the whole material. Okay, so that's the reason why I'm saying this is that I added this sentence to this slide to make sure that you all know what the orphan is. But let me explain what the situation is. We got three processes, P, Q, and R. And they are sending messages to each other. And the ones with this dot at the end are the messages that have been logged. Okay? Logged at the sender side as well as at the recipient side. Now watch this message M2. That one is not logged. It's just sent, nobody takes care of it, and it's being received by Q. Then Q sends this message M3 and logs it. Okay, so far so good. Now Q crashes over here, and later on recovers. It says to these guys, hey guys, I just started anew, so I'm not going to roll back to my checkpoint. Can you replay your behavior to me? And by that I mean send me the messages that you sent before. Now the problem is that it can tell so to P, and P will retransmit its M1. Good, because don't forget, what will happen is that this guy from this point on will replay its own part of the piecewise deterministic interval. Okay, so that part is just like adding a bunch of numbers, and then it was waiting for a receive statement. And it gets this message because that message is being replayed by P. But now the problem is that it can find in its log that it sent this thing over here, but hey, nobody's going to replay M2. And what basically happens is that process R receives and subsequently delivers this M3, but now becomes an orphan when Q recovers. Okay? Because this part of R is gone. So R is now doing stuff that it may not even be supposed to doing because Q recovered and is not doing what it was doing before. And R is now orphaned because it was first dependent on Q. But Q says, well, I don't know you anymore. That's the whole idea. And that's what you want to avoid. And the question is, how can we avoid it? So the question will be, when do we exactly log messages? Yes? What about the sequence of the events earlier?
Yeah, we're now clear that M1 happened before M3, but the read messages, there is no Q state.
Oh, okay. So let me try to repeat your question. So here it's clear that M3, the sending of M3 occurred after the reception of M1. That's what you're saying. That thing was logged, okay, but what should happen is that in this case, it would receive M1, it would look into its log and would hopefully find this M2, but it's no longer in its log. And then it finds this M3 over here, and it sends M3, and it's totally unclear whether it should have actually have done it. If M3 was dependent on, let's make this following assumption. If M3 was dependent on the reception of M1 and M2, in the execution of Q, it may now happen that M3 will not be sent. That's the problem. Does that answer your question?
That states that there is a problem, but there is no answer for that?
Yes, there is an answer to that. And I'll come to that answer by the last slide. The answer is you log everything, and then you execute your state interval until you reach this point where you should have this non-deterministic event, which by now has been recorded, and you make sure that that event is then replayed, like the sending of a message. Okay? And that brings you, this is the most important observation, that brings you back into a state just before you crashed. And if we make the assumption that the crash was caused by an external event, okay, like let's say that your hard disk just broke, then you just came to a state and now you're fully recovered and can proceed as before. Okay? Now, this is a bit tricky, but just a few more slides and then you're done with it. But you have to pay attention to this. Yes?
What, for example, you want to avoid crashes which are not due to hardware, but due to synchronization and...
For example, because of a bug. Yes? Well, that's actually a very nice question. So suppose this crash was caused by a bug. And you play the game again. What will happen? You crash again. Okay, so that's not going to work. So the hidden assumption here is that you at the very least fix this bug, or that what may happen is that you run it a couple of times and you come to the conclusion it must have been a bug, and then you have to change things. Yes?
Right, but what, for example, if you have a system which, well, doesn't have so huge bug, but the fix is not perfect, so in some occasion,
Oh.
go to a deadlock.
Well, deadlocks are not a crash. So what happens is, I'll repeat your question. If you essentially have intermittent failures, they happen, but not necessarily all the time. To give you an example, laptops are known to become very warm, and they actually lead to many intermittent failures. Namely, sometimes they crash, sometimes they don't. Okay, so basically, if you replay the thing, you won't notice anything. Well, that's okay, because if that happens, that means that if you start replaying this stuff over here, you won't reach this crashing anymore. You'll continue, and that's fine, until that, not really a bug, but that problem with your hardware pops up again, and then you crash again. Okay? This is a very good point to address the following, and I haven't mentioned this before. There are bugs. Okay, so how do you fix bugs? Some years ago, there was, I still think, a really fantastic paper presented at a conference, SOSP, and they did some very interesting experiments. They took programs, and some of these programs crashed, and for good reasons. For example, a buffer overflow. And what they did is, well, first of all, they made the observation that many programs have a finite life, in the sense that you just run them until completion. So an operating system does not fall in that category, right? An operating system never completes, so to say. But take a look at the programs that run to completion. And now you have a program that has a buffer overflow. So what you can do is you can try to fix that bug. What you can also do is make the buffer a bit bigger. Okay? I know it's not a solution. What they did they examined many of these types of problems, and they fixed the problem by these engineering solutions. Got a buffer overflow, let's increase the buffer. 95% of the failures that they saw before vanished. They did not occur again. And I found that very interesting, actually, because if you realize how we treat patients, or how the doctors actually treat patients, they try to diagnose what's wrong with you, and in all fairness, they know more often not what is wrong with you than that they do know what's wrong with you. And the effect of this lack of knowledge is that they give you medication, right? And basically, they don't say this, but this is what they do. Try this. And you try it, and if it works for you, hey, you're happy. But the problem is that, your next door neighbor who has exactly the same symptoms, this person also gets the medication, and my God, it doesn't work at all, okay? And, well, in that case, hey, they try this one. And this is what they do. They try. And in many cases, it works. And in so many other cases, it really doesn't work. And these guys said, well, this is how you can not necessarily fix programs, but you can make them work again. And is it good? Is it bad? Well, by the tone of my voice, you can probably think, well, he doesn't think it's necessarily bad. And I think that's true. There's no such thing as a healthy body, and so there's no such thing as a healthy program. So let's fix it in this way. And it's extremely cheap. Important assumption, a program has runs until completion. So that's an assumption, yes?
R is named orphan because it didn't relay a message it was supposed to.
R becomes an orphan because stuff happened over here. Q is still running and is recovering, and was supposed to do this to bring R in sync again with Q, but that's never going to happen. So R, I can reformulate it like this. R was dependent on Q. Q rolled back to a state, and what we didn't do is maintain that dependency. Okay, so R, could be argued, may now be doing something completely independent from Q that it shouldn't be doing in the first place. That's the reason why it has been orphaned. It has been decoupled from Q. Okay? Q can be also an orphan, but you also always become an orphan if another process crashed and let you down. So it's really like I just said. You're not reinstalling the dependency that there was between Q and R, and that turns R into an orphan. Okay? What? Well, you don't want to know when you become an orphan. You want to prevent becoming an orphan. And that's what I'm going to explain now. Okay? It's no use in knowing what you are if that's not what you want to be. Okay? You just want to make sure you never become that what you don't want to be. This is not philosophy. Okay, so what we'll do is we'll talk about message logging schemes, and I have 3 notations here. The header of M, M is a message, is the header of a message M containing its source, destination, sequence number, and delivery number. If you need more information, you put it in that. The idea of header M is that it contains all the information for resending a message and delivering it in the correct order. There is one important assumption. The data as part of the message is reproduced by the application. So what you're seeing here is that I'm making a distinction between what the middleware is responsible for and what you can ask the application to do. Is this bad? No. Think about failure transparency. I argued that it's almost impossible. It is theoretically definitely impossible to have full failure transparency. So you may actually get the application involved like, hey, something went really wrong. You need to replay part of your code, like producing the data for the message. Okay? Dependent M, one thing. A message M becomes stable, very important, if its header can no longer be lost. For example, because you safely stored it away. You put it away, and by safely, I mean, in the book there's something about stable storage. It really cannot be lost. You can, nowadays make stable storage by just buying a €100 hard disk. Whoa, did I say that? I just said that. In principle, you could do it. But you get the point, okay? Depend of dep M is a set of processes to which message M, as well as any message that causally depends on the delivery of M, has been delivered. And I should actually replace this with potentially causally, okay? Because the distributed system never knows about real causality, but it can suspect that one message is causally dependent on another. Yes? Does this result in a very large set of dependent processes? If you have an intricate computation with lots of processes, yes. So where would you typically see this in practice? For example, in a K-fault-tolerant process group, where you have 5 processes, checkpoint is expensive, and then this may be a bit cheaper. But I'll come to that, back to that in just a minute. So does it scale? No, it does not. Okay, does it have to scale? No, it doesn't have to scale, because it's often just used in the context of fault tolerance. And copy M is a set of processes that have a copy of the header, but still in their volatile memory. Yes? The sender. The sender. Because you will ask the sender to replay things. You could, I'll just keep it simple, we'll let the sender store it. You could also let the receiver store recovery information. Excuse me? Then there would not necessarily be a need for retransmission. Yes. But I'm assuming that, for me, the most important part is that the message is stored and that you do want to replay it. But in fact, I won't be even talking about replay over here. Okay. We have a collection of crashed processes. Okay? A non-crashed process becomes an orphan if there is a message such that Q depends on that message, right? But it has a copy, but the copy of that message is completely stored in the crashed processes. Can anybody translate this to me?
Q is dependent on the message, but the message has not been stably stored.
Exactly. That's what this says. So here you have your orphan who is doing stuff because it depended on this message M, and all the information on that message M and the causally related processes based on that message have just crashed. Poor Q. So what you want is that for all messages and for all sets of crashed processes, that if all the information on that message has been lost during the crash, then all the processes that depend on that message have crashed as well. I could reformulate this. They belong to this set of crashed processes. Because then, hey, everything's lost, including the processes that depend on it. Okay, who cares? No harm done. Got it? But I won't have any orphans. Now that is mathematically the same as that for all messages, the processes that depend on that messages are always a subset of the processes that have a copy of that message in their volatile memory. Okay? So nor orphans means that for every message M, we maintain this relationship. And I just need to make sure that this is the case. And then I don't have to know who is an orphan or not, because I will prevent having orphans. Now there's a pessimistic way of doing this. For every non-stable message, that means it's not written to storage, there is at most one process dependent on that M. Okay? The consequence is that an unstable message in a pessimistic protocol must be made stable before sending a next message. And there you see it. You send a message, but you don't want to have any dependent processes floating around later on. So what you do is you make that message stable by putting it in your log. And that means that you can always replay it. But the most important thing is you won't be taking the risk of an orphan process. So the observation here is that the single recipient M can now safely crash. It's the only process that depends on this message, right? Because otherwise I would have already made that message stable. That means, okay, only the recipient now depends on this message, in the sense that if anybody crashes, then hey, it will always be exactly the set that depended on this message because I made it stable. So the recipient can now safely crash, bye-bye, and then it won't lead to any orphans. Got it? Are you all with me? Is this clear to everyone? Yes?
It's not perfectly clear. I would try to violate the protocol and let's see if we can prove that we have no orphans.
Oh, you mean an optimistic protocol?
Yeah.
Sure. So let's do an optimistic protocol. So an optimistic protocol, you do something else. For every unstable message, we simply ensure that if all the information on that message was lost because of the crash processes, then we'll simply ensure that eventually the processes that depended on that message also belongs to the crashed processes. You see where I'm heading towards. This is indeed the set of processes that have been marked as faulty, crashed, okay? So the consequence is to guarantee exactly this. We generally roll back every orphaned process until it no longer depends on M. That's a nice way of doing it.
So you're saying we are killing processes?
Not yet, not yet. So this is what I'm saying. Here, this is the nice way of doing it. So Q has just been orphaned. Ah, poor Q. Now I can do two things. I can roll back Q to the point that it is no longer dependent on M. Okay? Now that's really the nice way of doing it. Got it? Because essentially what I'll be doing is I'm removing a live, I should say a non-faulty process from this set dependent on M, where I had the constraint that the set of processes depending on M should always be crash processes. So I can do two things. I can remove it from that set of processes that depend on M. I can do that by rolling back. So I'm taking Q out of that set of processes depending on M. Or I could do the other thing, crash Q, meaning, hey, I just made sure that we don't violate this rule. So it's either crashing Q or rolling it back. Okay? And you suggested that this would be an optimization. Now, what you see in practice is that you always implement the pessimistic protocols. They may be a bit slower, but it's so much simpler. And, you know, just crashing healthy processes is generally not considered a very good idea. Okay, yes?
Crashing and rolling back is not the same.
Crashing and rolling back is not the same.
When it comes up to rollback, right?
No, Q didn't crash.
Yeah, but
Q was living a happy life.
crash it.
Hmm?
But we are going to crash it, let's say. It's the same as then rolling it back, because after he crashes, you will come back and roll back.
No. Okay, now I see your point. If you crash Q and then let Q get back into recovery mode, it will recover way before the point of being dependent on M. Okay? And rolling back Q allows you to roll it back to the point where it has just not been dependent on M, and then let it continue its life. Yes?
If we roll back Q, we also roll back all other processes to the points.
If we roll back Q, we will have to roll back perhaps other processes as well. Well, it's it's not because you're rolling back Q. What you will be doing is that Q may not be the only process dependent on M, so you may have to roll back other processes. And what you do need to take into account is the dependencies between the processes that you're rolling back. But rolling back isn't that bad as long as you still have your consistent recovery lines. Okay, so in principle, you never need to roll back further than a checkpoint, such that the group of checkpoints that you will then have still forms a consistent recovery line. Now, the question you could ask yourself is, doing all this administrative work not much more expensive than a simple message logging scheme like the pessimistic one in combination with checkpoints? And that is actually the case. And that's the reason why, if you do this, you actually do pessimistic logging, because it is the cheapest for logging back and replaying. But in all fairness, I always say this, I think every year by now, this work is based on a survey written, a very good survey written some years ago. And by coincidence, I met the author at a certain point. I didn't know he was the author of that survey. It's a well-cited paper. And at that point, he was working at Microsoft. And then at a certain point, we got to talk and say, "Oh, wait, you wrote this article, and I'm using that in the book." And then he said, "Okay, let me tell you something." He said, "I'm now working at Microsoft. You know how we do these things?" "No." He said, "We don't." Basically, I mean, in industry, you do even more practical things. You will have, I'll call it application-specific recovery protocols. Say, okay, if the going gets tough, you have recorded stuff, and you may be using checkpoints. You will definitely do this for processes that will go on and on and on, so that you can recover. But if the going gets tough, you just reboot. And in fact, there has been a line of research for some number of years where they say, let's just recover by rebooting. And what you then do is you design your parts of the distributed system in such a way that you can do very, very fast reboots. And of course, what you often do is that all the critical information that you really rely on, not in the dependencies between the processes, but the data that you're processing on, that is stored safely in disk. And then when you do reboot, you read from disk what you had already been doing, and then you continue what you were supposed to do. And it turns out that that's actually a very practical solution.
Is this Estonia stuff? You shoot the other node in the head?
I don't know. This terminology I'm not familiar with. You want me to record this?
Stonet is for nodes virtualization cluster. If you have a whole node and you can assert a failure at that node,
Yeah.
or you are unable to determine the state of the nodes or what the node
Yes.
is actually doing, you just kill it. It's somewhat related, but it's more on the node computer hardware scene level than process level.
And this is called
Stonet, shoot the other node in the head.
stone in the head? Stone at the head?
Shoot the other node in
Shoot the other node in the head. I think I like orphans better, but but okay. Welcome to computer science. So, shoot the other node in the head is a deliberate knockdown of another node because you really can't trace whether that node is actually causing the fault. That's what.
Well, you don't know in which state the node is. So, for example, if you have a virtualization cluster, one node fails, you don't know are the virtual machines still running on that node.
Okay.
Bit break,
Yeah.
kill it.
Yeah. So.
You usually vote for that, so you don't kill
That's kind of a decent way of shooting another node in the head. Okay, so basically what you do is it's the cost of determining what the state is of that node and trying to recover with that knowledge is so expensive that you just say poink, and then you take it from there. I think this is a good time for a break.